Welcome back. Hello, we are talking again about artificial neural networks. And in the last video, we talked about what they are composed of, these artificial neurons, and we compared them a little bit with biological neurons. And what we will do now is to look at how one perceptron, one of these artificial neurons, actually works. And as an example, we will take a logical function like a logical AND. These logical functions are nice for demonstrating how things work because you see you have two inputs, A and B, and you have A and B, what comes out if you want to make a logical connection between A and B. So what does this mean? AND is defined in logic as being true if both of its inputs are true. So if you say, I ate an orange and an apple for dinner, and an apple. This is only true if you actually ate an orange and an apple. This is what this so-called truth table is showing you here. 1 means true, 0 means false. If you just ate the orange, or if you just ate the apple, or you didn't eat any of them, then the result is 0 because you're not telling the truth. So this is what the truth table does. It tells us what it means to say and, right? It essentially defines what and means. And so now when both inputs are 1, true, then we want the output to be 1. We want the neuron to fire. If one input is 0 or both inputs are 0, then the whole thing should not fire. And this is the behavior we want. So how do we achieve this now? With an artificial neuron, with a perceptron, we first make this table. We realize what it is that we want. And now look at this structure here, which I have on the screen. And you see that you have 3 things that you can change in this neuron. You cannot change the way it processes information. You cannot change the fact that the synaptic weights are multiplied with the input. You cannot change the fact that it adds up the inputs. And you cannot change the fact that it compares with the threshold. But what the variables are, what you can change, is how much are your synaptic weights, how much do you multiply each input with, and how much is your threshold. And these are all the variables you have. And by changing these variables, you can make your neuron perform like a logical AND. Now think about it. How do you do it? If you have something that should only fire on the right side if both inputs are 1. Let's say we put the synaptic weights at 0, right? Put them both to 0. And put the threshold at something halfway, let's say 0.5. So now I have 1 and 1 coming in on the left side to my neuron, because I want to do the first line of my truth table, and I want the output to be 1. Now if both my weights are 0, what will arrive at my neuron is 0, because 0 times 1 is 0, and the other 0 times 1 is also 0, so I will get 0, and then when I add it up, it will be 0, and so this will be less than 0.5, so my neuron will not fire. This is not what I want. I want it to fire, right? Let's say I put the synaptic weights to 1, each one to 1. So now I get 1 and 1. I add them up is 2. 2 is bigger than 0.5, so yes, it will fire. So I have sorted out my first line of my truth table. Let's go to the second line, 0 and 1. So A is 0, B is 1. Now, what will happen? 0 times 1 is 0, and the B, 1 times 1 is 1, so the sum is 1, is bigger than 0.5, so it will fire again. This is not what I want. It does the first line correct, but it does the second line wrong. What do I want to do in order to improve this? I want to put the synaptic weights perhaps somewhere halfway. Not 1, but a little less. How much less? If you think about it perhaps for a moment. Where do you put the synaptic weights in order to get the behavior we want? You have to put them so that the sum of A and B, because this is what the neuron is going to do, it's going to take the sum. The sum is greater than the threshold, but one of them alone is not greater than the threshold. And then it's easy to see if I say, for example, my synaptic weights are 0.5 and 0.5, and my threshold is 0.6, I just take something that's clearly bigger so that I don't have to deal with these edge cases of being equal, the threshold being equal, should it then fire or not, right? We don't want this additional complication. So we'll just make it a little bigger, 0.6, 0.7, 0.8 will all work the same. So as long as the threshold is somewhere higher than my input weight, my multiplicator, I'm fine, and I get this function. Because now, look at this, if the synaptic weights are 0.5 and 0.5, and I have both ones on the input, then I get 0.5 and 0.5. The sum is 1 is greater than 0.6 or 0.8 or whatever I put there, and I get an output. If only 1 is firing, or 0, then my output will be either 0.5 or 0, which is lower than 0.6, 0.7, 0.8, my threshold, whatever I want. See, it doesn't really matter. And I will get 0 on the output. And that's it. That's all. And so now I've finished. If you want an exercise for fun, try to think how would you do it to get it to calculate a logical OR. The logical OR is different from the AND because you would have a 1 on the output, a firing on the output, whenever one of them is true or both are true. So you would have here in our diagram 3 lines of 1 in the output, and only the last one line would be 0 when both are 0, when both inputs are 0. So try to do it. Try to see if you can configure your neuron to do this. It's very easy. You just have to change a little the threshold and the synaptic weights. Okay, so this now is a neuron that actually does some processing. And with this, you can already build a computer. You know, a computer is nothing else but a machine built up of these logical gates. So if you have an OR, if you have an AND, if you have a NOT, if you have an OR, with this you can build any computer already. But this is much more powerful, and we will see later why it is much more powerful than a normal computer. And I give you a hint now because we were just talking about it, because it can deal with inputs that are not precisely what it expects. So you saw that when I add up, I have this range of the threshold, and if it's smaller than the threshold, wherever it is, it will not fire. If it's bigger than the threshold, wherever it is, it will fire. So it doesn't care about the specific number that comes out of the summing up of its inputs. It only cares about the general idea. Will it be more or less? And this is important because this allows us as humans, if you think of your own cognition, to recognize similar things. For example, you can recognize my face now with these lights. I can change the light. I can, switch that off, for example. Now my face looks very different, but you can still recognize me. I can switch it on again. I can take off my glasses. My face again looks very different, but you can recognize me. I could cut my hair. I could change my t-shirt. I would look different every time, but you can still recognize me. This is a kind of magic that we do. And it's very difficult to do in a computer because in a classic computer program, you have to say what you're looking for. I'm looking for the black t-shirt, the white hair, and so on. And if these things are not there, then your program will not recognize me. But a neural network will. It is tolerant to some extent of changes in the input, because different inputs will still map to the same output because the threshold has this flexibility, right? It doesn't matter if I have precisely a particular input. I can have an input that's similar, and it still will lead to the same firing. So that the dissimilarities in the input, the variance in the input, gets absorbed by this neuron and is not passed on to the neurons down the line. So it stabilizes its input. It identifies an input and sticks to it. This is how you could describe what is happening on a qualitative basis. And this is very important, this ability of the neuron to work with different inputs and to recognize them as the same thing. And this is what our cognition is doing. This is what all organisms with the nervous system are doing. This in itself is not yet a really useful thing, because what happens now is that we have to program our neuron ourselves. You don't want to do this. You want your neuron to be able to learn by itself. You don't want to be the human who has to adjust all these synaptic weights by hand. Because if you think about it, if you have, 10,000 neurons, and this is a small neural network, 10,000 neurons, you have 10,000 neurons, means they're all connected to each other. And then after you connect them all to each other, perhaps in multiple layers, then you have 10,000 times 10,000 times 10,000 synaptic weights. And now you have to adjust manually each one of these thousands or tens of thousands of synaptic weights in order to reach a particular outcome among, very complicated outcomes like recognizing a face. How do you even go about that? How do you adjust the weights to recognize a particular face? This is a horrible task, right? We cannot do this. It's impossible for us as humans to do it. So obviously we need the network to learn by itself. We need a computer program that can adjust the weights as we want them and produce the desired result. And this is called the learning algorithm. So the learning algorithm is the program that adjusts the weights of a neural network so that it completes a particular task. And we will talk later about exactly how this works. So don't worry about this now. You just need to know that we are not normally doing this, that we adjust the weights by hand, because this is not going to be successful. Okay, I think we can stop here. And in the next one, I will show you a simulation of a neuron where you can adjust the weights and see how it actually works. See you there.